So let's move to the astronomer proposal tool, the APT. The APT is the software that you need to use to submit a James Webb proposal. Okay, it's a template-based software. There are 17 different templates, basically corresponding to different instrument configurations. The APT does a lot of stuff. It calculates the exposure time, how much integration you have, also the overheads. It calculates the schedulability of your observation, depending on the RA deck and the date of observation that you need. It also computes the actual charge time that includes the overhead for your proposal, so how much time you request for your proposal. And very importantly, the APT has the final say. So we've talked about the exposure time calculator just now. We've talked about the target visibility tool, but actually what the APT says it is, that's what it is. It has the final say. That's the tool you use to submit your proposal. Luckily, they are pretty much in sync with each other, but there may be some differences and the APT wins. Okay, so the APT, you need to install it. It's found on the Space Telescope Science Institute webpage. Make sure to always use the latest version because there's lots of development going on and lots of versions happening. Also, you can find the documentation about the APT on the JWST pages. All right, so I'll give you a quick demo of how this APT tool works. I'll first go and launch the tool. That's what it looks like. It was designed for the Hubble Space Telescope proposal, so they simply ported it to James Webb. So I'll create a new James Webb proposal. All right, so we have the front page. Okay, this is where you enter different fields. So you need to enter the title of your proposal, the abstract. The category, is it a general observer, early science, early science, or DDT, or guaranteed time observation? For you, it's going to be the GEO. It's going to be cycle 1, and then here you have two numbers that are filled in by the software. Is the science time? It's how much actually photon time, how much integration you're doing. And the charge time, the actual wall clock time it takes to execute the observation. So you try to be efficient. You try to get a good ratio here of science versus charge time. All right, you can change if you wanted the proprietary period. By default, it's 12 months. And there are other categories like scientific and keywords that you can input. Keep in mind that you have nice red X's everywhere if you don't fill them, if you don't fill the fields. When you submit a proposal, of course, all those red X's need to not be there. They need to disappear. You need to actually fill those and make sure there's no red X. A proposal can be submitted with yellow warnings, although we don't recommend it, but you can still submit with yellow, but with reds, it will prevent you from submitting. All right, a very important section is the PDF attachment. That's where you put an attachment of your scientific justification and technical justification and figures, references, and all those important things. The actual length of the justifications and so on is going to be defined in the actual call for proposal, November 30th. And yeah. All right, so let's move to the next section. The proposal description, the observing description. Here is where you will briefly describe the observing strategy and any special requirements that you have for your observation. Then you'll put your name as PI. So in order to do this, you need to have a Space Telescope account, and here I have one. So you can select your account. If not, you have to create one. Then you can add co-Is. by doing the same thing. Here I will not have COI, so I will delete this by right-clicking if I can. No, I don't seem to be able to. Anyway, I usually could. All right, so let's move to the target. We'll add targets to our program. There are a few ways to do so. The most used are the fixed target. So you can either use a name resolver or an actual array deck if you already know the array deck of your target. In my case, I will use the fixed target because I know that my target NGC891, I know it's NGC891, I know its position, so I will use the same name here. You have to enter the category, it's a galaxy. Okay, so let's fill in the array deck. So in my case, I had this 42.4. Remember, that's the coordinates we used in the ESA Sky viewer. All right, it's an extended target, yes. I can define a background target if I need to do some sky subtraction, for instance in MIRI with the IFU, but not here. Very important here, the proper motion. If you have you need to fill that section. It will not be automatically filled even if you had resolved it with Simbad. If you're looking at the stellar source, you need to move to put its proper motion here. All right. So the next thing we'll do is create an observation looking at a target. So let's create a new observation. Okay, so in that new observation, I can give it a label, NIRCam, NGC891, and I have to add. Okay, so this window tells what observations I'm doing with this. I can actually create the details of it here. So I'll select an instrument, NIRCam. I'll select one of the 5 templates available for NIRCam. So imaging, choreography, all this. I'm going to use imaging. I will select my target. Okay. You have the possibility here to create a coordinated parallel program that is use another instrument at the same time as what you're doing. This is a whole new another feature that we will not go into today. But if you're interested by coordinated parallel, you can simply click here. There's a question mark. You can click and be redirected to the JDocs page about coordinated parallels, and you can read about this. Okay. Okay, so I'll go back. And I'm looking here at the visit splitting distance. This is actually important to keep a track of. Okay, that's the distance at which, if you move to do DITR, if you move beyond 65 arc seconds here, the APT will split your observations in 2. And those 2 could be observed not necessarily one after the other. They can be observed at separate times, and it will cost you like 30 minutes more to salute twice. So try to keep within the splitting distance. All right. Let's now put the details of the actual observing. And I'll first select how many of the modules I use. The 2 of them, only one or none. I'll use both. I want to cover them as much field as I can. The subarray is the detector size that I use. Do I use the whole detector pixels or just the subarray? If I use both modules, that means I'm interested in wide coverage, so I need to use a full subarray, the full array. All right, and then I select my dithering strategy. There are there's quite a lot of different dithering strategies with NIRCam in particular, depending if you want to cover the gap between the two modules or just the gap between detectors. And so I'll select one of them. You can, obviously, you're invited to read about them on JDocs. I'll select 3 positions in my ditter pattern. The size of the ditter is going to be small, and I will not do any sub-pixel dithering. And yeah, and then I can add the filters I want to observe with. NIRCam, remember, can see simultaneously 2 wavelengths, 2 filters, a red channel and a blue channel. I'll select my blue channel first, the short wavelengths. I'll select a wide filter. Then for the long channel, I'll select another filter. Here, I have to define what kind of readout pattern I use. Again, you're invited to read about those on JDocs. I can use, say, the medium, and it's going to be used for both long and short channels. Okay, I'm going to do how many reads or how many groups in that in each integration. I'm going to do 5, say, and I'm going to do, say, only 1 integration there. All right, so you can see that the total exposure time for the 3 ditters total together is 1300 seconds. If I had used no, if I had used no ditter and exposed only for a single integration, that number is divided by 3. So you see that the reported total exposure time is for all of the ditters together. You can go back in the proposal and look at the science time that you're charged. And you see here, you're using 0.38 hours of time integrating, but to get there, it requires 1.3 hours total for your proposal. That's because slewing to the target takes about 30 minutes, and there are many different overheads, the instrument configuration overheads and acquisition overhead that you need to consider. All right, so I'm in my observation, and now I said I wanted to have the NIRCam mosaic along the galaxy NGC 891. So in order to specify this, I need to use the Special Requirements tab and actually explicitly ask for this. So I have to add a new constraint, and there are many different constraints you can put. There's a timing constraint. It can be between dates. It can be between phase of say, a transiting planet, for example. It can be linked to other observations in my program. For example, observing target 2 after target 3, and then coming back to target 4, for example. But here I will just use the position angle constraint. I have a range of position angle that I'm willing to use. I said it was between 90 degrees and 105 degrees. Okay. So this is the instrument position angle, aperture position angle. It's translated to the observatory V3PA position angle here. Okay. Now, I've been all along in the form editor. Now is the time to move to another icon, the visit planner, to see if your target is schedulable and for what period. The first time you go there, you need to update the display, or every time you change something in the form editor, you need to update display here. It will calculate the constraints. There are many different constraints here. So it's basically your observation, as we see here, can be observed at the end of December and beginning of January, as we saw earlier with the target visibility tool. There are different constraints. The guide star constraints, for example, gives you this, but basically it's the position angle special requirements that you put that constrains the period to a shorter period than usually. So if we had removed this constraint, so let's go back to the form editor and let's remove the special requirement constraint, for example. Okay, and then go back to the visit planner and do an update. You see that if we're willing to observe the galaxy at any position angle possible, then the schedulability is bigger. Okay, so be cautious to not over-constrain your program with this. All right. One of the last things I want to mention or show, well, first, you can, of course, do a PDF preview of your proposal, the whole proposal, and you can use this, this tool here to actually submit. I will not try this today, but you can go back to view your field in Aladdin. It will open an Aladdin window. So we've already got acquainted with the field by using ESSSky, but you can do it as well with Aladdin. And with Aladdin, if you want, you can even, so we'll overplot DSS field. There you go. Okay. And that's, so here, remember, I removed my PA constraint. I can put it back. Let's put it back. Special requirements. Add position angle between 90 and 105. Okay, and let's go back to Aladdin, and you see that the field is correctly oriented. You can see this by overplotting the orient range, for instance. I'll zoom a little bit. Okay, you see that it's the green range is where you're aiming for. If you want, you can feedback, make changes to the position of your field. Say like this, I want to change that, and you see that it speaks to the APT, and it gives you the new position. So, if you go back to the target, remember what our target position is. It is 222.40.8 and 42.24.0. So if we go back to Aladdin actually this here, we change slightly the position. We can commit the changes. Okay, and when we go back to the form editor at the target, the position has changed. Last feature I wanted to highlight is the guide star availability. So if I go to my visit planner, okay, some programs, if you're some targets that are in very sparse fields could be missing guide stars or could be close to missing guide stars, and you may get an error and you don't know why you can't schedule this target. So I'll show you an example of with this example that it's not the case. In this case, you can observe it. There's plenty of guide star. So the guide star constraint is this one. You can get a report, the guide star availability, and here you have the position angle plot as a function of time that we've seen before, but we also have this is the number of days where you can, when you have available guide stars as well. So there's, I think I wanted to show something else. It's another report I wanted to show. Guide star for visit. No, it was this one. So there's a, there was a plot with the number of guide stars available per Okay, well, we'll try to demonstrate this in future webinars. Okay, so that's it for the APT, and we're basically at the end of our demo of today's webinar, and I will tell you that next time we'll talk about imaging in more details using the ETC and the APT, and so we encourage you to install the tools, the target visibility tool, and also very important to create a MyST account with STSCI to use the ETC properly, and install the latest version of APT. All right, so in the name of Julien Rameau and I, thank you very much, and see you next time.